when we look at change in enthalpy, delta H, that's for a particular reaction with particular coefficients. If we change the reaction, then delta H changes also. So we're going to look at how can we manipulate these things. So if we take our chemical equation and we multiply by some factor, multiply by 2 maybe, then delta H is also multiplied by the same factor. So if I react 1 mole of A and 2 moles of B, and I get delta H some amount of energy. If I react twice as much stuff, 2 A's and 4 B's, I would expect twice as much energy, right? Does that make sense? You burn twice as much propane, you get twice as much heat. You burn half as much, you get half as much heat. So that's what that one is saying. If the chemical equation is reversed, then delta H changes sign. So here, if A reacting with B gives off heat, then if I do the opposite and I have C reacting to form A and 2B, that must absorb heat, right? Because you can't create or destroy energy just by making a reaction go forwards and backwards. It'd be really cool if we could. That would solve our energy crisis, but we can't do that. So reverse the equation, change the sign. And then Hess's law. And you should try to remember this name, Hess's law, because it's going to come up a couple more times in this class, and it'll also come up in Chem 1B. And this is the idea that if you can express a chemical equation as a series of steps or a series of reactions, then delta H for the overall thing is the sum of the delta H's for each step. So here I've got A reacting with 2B to make C, and that has some energy change. And then that C is going to go on and react to form 2 D's. That's going to have another energy change. When I add these two chemical equations together, the C's cancel out, right? And I get A plus 2B going to 2D. This is the starting point, and this is the ending point. This was in the middle, right? But delta H is a state function. It doesn't depend on how you got there. So it's going to be the same energy if we start here and go straight to that, or if we look at it going in steps. And so this is an energy diagram trying to illustrate this. So here we have our reactants. They have a certain amount of internal energy. And when they react to form C, they're taking energy in from the surroundings and gaining energy. When C reacts to form D, it releases a lot of energy into the surroundings. So the overall change is this distance here, which is this positive number plus that negative number. This is just like elevation change, right? If this is the top of the mountain and I'm going to go down here, it doesn't matter how I go. I could, go down on skis, or I could slide down on my butt, or I could fall head over heels. Or I could take a helicopter and go way up into the sky and come over here and come back down. And everybody else has bumps and bruises, and I'm just feeling good. Change in energy, change in elevation is the same. Any questions? This is awesome because it makes it possible to find delta H for a reaction without actually needing to do the reaction. Some of the reactions are very difficult to do and measure energy changes. So if we can find reactions with known delta H's that we can add together to get the overall final reaction, then we can get a good estimate of delta H. So we add the reactions to get the reaction of interest, and then delta H for that reaction will be the sum of all the delta H's. Consider the following chemical equation. 2A plus B goes to C. Delta H is 122 joules. Is this an exothermic or endothermic reaction? Endothermic. This is a positive number. Money coming into my account, I'm the reaction, is positive, right? So money's coming in, energy's coming in into endothermic, okay? That was just a little bonus review. So what would it be if we have 2C going to 4A and 2B? What we have to figure out is what changes were made. How did this change to become this? What's one thing you see? It's reversed, right? Here C was a product, and now C is a reactant. So then what do we do to delta H?
Make it negative.
We change the sign, right? So now we've got negative delta H after changing the direction. What else happened? It was multiplied by 2. All the coefficients are twice as large as they were there. So then we're going to take that negative, we made it into a negative, and we're going to multiply by 2. So it was positive 122, make it a negative 122, multiply by 2, negative 244. Did you follow it? We're not doing any crazy math or anything here. The hard thing is this is so abstract, right? You can't see this happening, right? And so we have to get comfortable with using letters in the equation like this as kind of a visual for what's happening, and that takes a while. Yeah.
Are we gonna do this like with an actual chemical?
Are we going to do this with an actual chemical reaction? Yes. Look at the screen.
Oh no.
Yeah, we did it with just letters first, but yeah, we are going to do it with real ones. Okay. So this is asking us to find delta H for this reaction. And it's saying use these reactions with known delta H's. Now the nice thing about these problems is they're going to give you all the equations that you need and only the equations that you need. If you were doing this just for finding something unknown, you'd look online or you'd look in the CRC and there'd be pages and pages of equations to choose from. So we can be thankful for that. We just have 3. So how do we do this? I need to figure out how I can add these 3 equations together to get this. So I'm going to do a little bit of highlighting here. So I'm going to highlight all the N2Os as green, because this is N's and O's everywhere, right? And it ends up with 3. No! My favorite molecule. No! So no is orange, and here's no, and here's no. And then we also have, maybe blue, we also have NO2. And so that's in there. That can just help us see where these things are because they're really similar. You can do this in kind of a haphazard way. I don't find that works very well. So this is what I would recommend. Look at your first reactant. Find the chemical equation that has that in it and make sure that it is on the reactant side. So here I have the N2O on the reactant side, so I'm going to start with that one. So I'm going to write 2N2O. I'm going to give myself a little bit of room. That's that green one. And then I'm going to write down delta H for it. Have I done anything to the equation? No, I'm just writing it down. So delta H is not going to change. Now, this does not have the same subscript that does, right? How can we change it so that it has the correct subscript? Divide by 2, right? So we're going to divide all the coefficients by 2, and we're going to divide delta H by 2. We might end up with some fractions. It's okay. They'll clear out later. So dividing by 2, that becomes a 1. This becomes a 1, and this becomes a 1 divided by 2, a 1/2. And then this is divided by 2. Okay? So now this matches up with that. Now let's look for the next reactant. That's the blue one, NO2. That shows up over here, but here it's a product. So I'm going to take this chemical equation and I'm going to write it backwards. It helps to keep your arrows lined up. So I'm going to write this backwards, right? So I've got 2 NO2 gas. That's this product becoming the reactant, and then these become the products. 2 NO and an O2. And I'm just going to follow up with highlighting those. So this is my other reactant. And then no is over here. Before I do anything to that equation, I'm going to copy down, well, I did something to the equation, didn't I? I'm going to write down delta H, negative 113.1 kilojoules is what it started as. I reverse the equation. What do I do to delta H? Change the sign, right? So I'm going to make this into a positive because it's going the other way. It's like, okay, I'm selling now instead of buying, right? It's just the money going a different direction. Is this the correct coefficient? No. How can we fix that? Divide by 2 again. So, that's me trying to move the screen and my fingers are too dry. So we'll divide that by 2, and we'll divide this by 2, and we'll divide this by 2, and we'll divide this by 2. Because half as much stuff reacting, half as much energy absorbed or given off. Okay, so I've got my green and my blue reactants with the correct coefficients. I have my orange product over here, but then I've got these other things in here. And I want to have 3 no's, and I only have 1. So this is where we're going to need this other reaction. This has 2 no's as the product, and if I add that in here, that'll give me the 3 that I need, right? So this is 2NO gas. That's the green. I say green and highlight in orange. That's the orange. N2 and O2. So I'm taking this chemical reaction right here. There's the N2 plus O2 to form 2 NOs. And I'm going to write down delta H. And it says delta H is plus 182.6 kilojoules. So I'm going to add these reactions together just like we did when we did the half reaction method of balancing redox reactions. Okay, and this is the same idea as doing like A plus B equals C, C plus 2x equals, I don't know, F. Two simple mathematical equations, and you can add those together. You're going to end up with A plus B plus C plus 2x is equal to C plus F. Right? You add everything on the left of the equal sign and everything on the right of the equal sign. There's a C on both sides. If I subtract C from both sides, it's still an equality, but I can pull that out. So that's what we're doing, adding the chemical equations. So hopefully, I'm going to do this. Give myself a little more space. So we're going to add these together. That's a good question. Doesn't this need a coefficient of 3? I've got it here in 2 different places. So when I add these together, I'm going to get my 3. Yeah, good question. So up here, I've got N2O. And that one's green. And I've got NO2. And that one we're highlighting in blue. And then I've got N2 and O2. These are not in my final reaction. So if I did things right, these should cancel out. So I have 1 mole of nitrogen on this side, and here I've got 1 mole of nitrogen on that side. So I can cancel those guys out. Maybe purple. So this and this go away. Because if this is making the N2, this other reaction is using it up, and so it doesn't show up in the overall reaction. I have 1 mole of O2 over here, and I have half a mole and half a mole. 1/2 plus 1/2 is 1, right? So these two added together are equal to that. So those are going to cancel each other out. And then what I've got left is my orange ones here. I've got 1 of them here and 2 there. And so that's going to give me 3 NO. Okay? Yes?
Why was one of the equations reversed and the other one not?
Why did we reverse one of the equations and not the other? Because one was backwards of what we needed. So this is where I think the highlighting is helpful. I want the green to be a reactant. So this, it was already a reactant, no problem. I want blue to be a reactant, but in this equation, blue was a product. And so leaving it as a product, I'm never going to be able to get the blue one as a reactant. So if I write this reaction backwards, reactants become products, products become reactants. So that's why I reversed this one. Does that help? Any other questions? So our chemical equation came out right. Now what we need to do is add up our delta H's. So I have negative 163.2 divided by 2 plus 113.1 divided by 2 plus 182.6 equals. So delta H overall is 157.55 kilojoules, and if we're going to be picky about sig figs, let's get rid of this mess up here. Delta H for that reaction is 157.6 kilojoules. Any questions? Let's do another one. This one only has two equations. Find delta H for this reaction. So again, I'm just gonna highlight my reactants. O3 and O2 look a lot alike, don't they? And here I've got H2, and H2 shows up there. And I've got H2O, and H2O shows up over here. These O2s are not in my reaction. I'm going to start with my first reactant and find an equation and make it such that it has 3 H2 as a reactant. So that's going to be this one. This has H2. So it's 2H2 plus O2 forming 2H2O. I did not reverse the equation, so I am going to not change the sign of delta H. Is that the correct coefficient on H2? No, I want it to be 3. What can I multiply 2 by to get 3? It's simple whole number fractions here. If I multiply by 3/2, would I get 3? So if I multiply this by 3/2, 3/2 times 2, the 2's cancel out and gives me 3. Yeah? And I'm going to multiply this by 3/2, and I'm going to multiply this one by 3/2, and those 2's cancel out. So then I also need to multiply this by 3/2. Everybody okay with that? You look a little skeptical. It's okay. Fractions are not most people's favorite thing. Okay, so we've got 3H2. This looks a little messy, but we've got it there. And then I need O3, right, as a reactant. So this other equation has O3 as a product. So I need to write it backwards, right? I need to reverse it. So 2O3 makes 3O2. And I reversed the equation, so I changed the sign on delta H. Let's keep up with our highlights here. There we go. So I used all my equations. Is this the right coefficient for O3? No. It's supposed to be 1, right? So if I divide by 2, which is the same as multiply it by 1/2, multiply by 1/2, these 2's cancel out. And multiply by 1/2, that's going to give me 3/2. And then I'm going to multiply this by 1/2. You can look at it as dividing by 2. It'll give you the same thing. So here I have 3H2. That was that green one. Plus, here's my O3, and these worked out to be 1. So O3 gas. Now we need to see what's going to happen with those unhighlighted things. I've got 3/2 O2 here, and I have 3/2 O2 there. Same amount on both sides. So we can cross those out. And then going to the other side, what I've got left over there is 3H2O. Does this match what I was trying to make? It does. So then down here, I need to add these together, taking into account what I multiplied things by. So delta H is going to be negative 483.6 times 3 divided by 2 plus negative 285.4 times 1 divided by 2. Negative 868.1 kilojoules. Any questions? It's just a lot of icky little details that you have to keep track of. And it's extra confusing when you have things like O3 and O2, and they kind of start to look alike. And yeah, so if you're a fan of using different colored pens, this is a great time to do